Geometric construction. This course will be completed in 4 sections. Now, let's do a brief review of previous knowledge. In the previous course, we learned dimensioning methods. We covered the basic principles of dimensioning, the components of dimensions, common dimensioning methods, and simplified notations, and mainly mastered the 3 key elements of dimensioning. Next, we will learn geometric construction. Teaching objectives and knowledge objectives. First, understand the connection between geometric construction and the expression of mechanical part structures. The accuracy should reach over 90%. Second, master the steps for commonly used geometric construction methods, such as dividing a line segment into equal parts, arc connection, drawing slopes and tapers, fitting irregular curves, etc. Clearly define the applicable scenarios for different construction methods. Be able to accurately distinguish the standard requirements for geometric construction in mechanical part drawings. The theoretical knowledge assessment should have a success rate of at least 95%. Skill objectives. First, be able to use drawing tools, compass, set squares, drawing instruments, etc., or CAD software to correctly complete complex geometric figure drawings, such as drawing the outline of parts with multiple arc connections, structures with slopes or tapers, and the precise expression of intersection and penetration lines of composite solids. The drawing accuracy should meet the national standards for technical drawing. Second, be capable of dimensioning horizontal, vertical, and inclined dimensions, as well as for circles, arcs, and spheres. Quality objectives. Develop the habit of strictly adhering to the Chinese national standards for technical drawing when performing geometric construction. Eliminate ambiguity in drawing. The occurrence rate of standard conformity issues in drawing reviews should be less than 5%. Establish a rigorous attitude that a drawing is engineering language. First, dividing a line segment into equal parts. Example 1. Now, we want to divide a line segment into equal parts. Let's assume that we want to divide it into 3 or 7 equal parts. Based on the knowledge we have learned before, we may measure it with a ruler. After measuring, we divide by the number of parts. However, if the measured length is 100 mm, and when we divide it into 3 or 7 segments, we will encounter a problem since it doesn't divide evenly. So, we need to use a geometric construction method to solve this problem. For example, here we have a line. We will divide it into 7 equal parts. We can draw an arbitrary line AM from point A. With a suitable unit length, we divide the line AM into 7 equal parts. Points 1, 2, 3, 4, 5, 6, and 7. Then, connect point B and 7. Draw parallel lines from points 1, 2, 3, 4, 5, and 6 to B7, and have them intersect with AB. This will divide the line AB into 7 equal parts. 2. Dividing a circle and constructing regular polygons. Use a set square and T-square to construct a regular triangle or hexagon. Example 2. Now, we will use a set square and T-square to construct an inscribed equilateral triangle, as shown, to construct an inscribed equilateral triangle inside a given circle. The steps are as follows. 1. Place the T-square firmly against the guide edge of the drawing board and secure it. Align the right angle edge of the 30 degrees to 60 degrees set square against the edge of the T-square. Move the set square so that its hypotenuse passes through point C on the circle's diameter. Let it intersect with the circle. This gives the intersection point A. 2. Flip the set square over. Align the right angle edge of the 30 degrees to 60 degrees set square against the edge of the T-square. Move the set square so that the hypotenuse of the set square passes through point C on the circle's diameter. Let it intersect with the circle. This gives the intersection point C. 3. Use a pencil to connect points A, B, and C sequentially along the ruler. This will give the inscribed equilateral triangle within the circle. Additional notes: if the set square's angle deviates, this can be calibrated by checking whether the 3 sides are equal, and whether the interior angles are 60 degrees to ensure the shape is correct. Example 3. Constructing an inscribed regular hexagon using a set square and T-square. The steps are as follows. First, place the T-square firmly against the guide edge of the drawing board and secure it. Align the right angle edge of the 30 degrees to 60 degrees set square against the edge of the T-square. Move the set square so that its hypotenuse passes through both ends of the circle's horizontal diameter. Draw 2 lines inside the circle along the hypotenuse. Second, flip the set square over. Align the right angle edge of the 30 degrees to 60 degrees set square against the edge of the T-square. Move the set square so that its hypotenuse passes through both ends of the circle's horizontal diameter. Draw 2 more lines inside the circle along the hypotenuse. Third, move the T-square up and down. Complete the remaining 2 sides. This completes the inscribed regular hexagon within the circle. Using a compass to construct the inscribed equilateral triangle and hexagon in a circle. Steps for constructing the inscribed equilateral triangle in a circle. First, use the circle's diameter endpoint F as the center. With the known radius r, draw an arc. It intersects the circle at points B and C. Second, connect points A, B, and C sequentially. This gives the inscribed equilateral triangle in the circle. Steps for constructing the inscribed regular hexagon in a circle. First, use the circle's diameter endpoint A as the center. With the known radius r, draw an arc. It intersects the circle at points D and E. Second, connect points A, E, B, F, C, D, and A sequentially. This gives the inscribed regular hexagon in the circle. 3. Arc connection, the drawing principle for tangent lines between a circle and a straight line. The method of smoothly connecting 2 adjacent line segments, straight lines or arcs, with an arc is called arc connection. The drawing principle for a circle tangent to a straight line is: first, the trajectory of the connecting arc's center is a parallel line to the given straight line. The distance between the 2 parallel lines is equal to the radius of the connecting arc. This distance is measured by drawing a perpendicular line from the center of the circle to the given straight line, and the foot of the perpendicular is the point of tangency. Next, drawing principle for circle-to-circle tangency. Let's look at the principle for circle-to-circle external tangency first. Method steps. 1. The trajectory of the connecting arc center is a concentric circle to the known arc. The radius of the concentric circle is equal to the sum of the radii of the 2 arcs, r1 plus r. Second, the point of tangency is the intersection of the line connecting the centers of the 2 circles and the given arc. Next, let's look at the principle for circle-to-circle internal tangency. Method steps. First, the trajectory of the connecting arc's center is a concentric circle to the known arc. The radius of the concentric circle is equal to the absolute difference between the radii of the 2 arcs, the absolute value of r1 minus r. 2. The point of tangency is the intersection of the extended line connecting the centers of the 2 circles and the given arc. After drawing, we can see that for circle-to-circle tangency, for external tangency, the distance between the centers of the circles equals the sum of their radii. For internal tangency, the distance between the centers equals the difference of their radii. Connecting arc and straight lines. First, use a circle with radius r to connect 2 straight lines. Example 5, as shown in the figure, given 2 straight lines forming an angle. This angle is not a right angle. It's required to connect the 2 straight lines with an arc or radius r. Method steps. 1. Draw parallel lines to the given straight lines. Determine the center of the connecting arc. The intersection point O of the 2 parallel lines is the center of the connecting arc. Second, with O as the center, draw an arc with radius r. The arc drawn is the connecting arc with radius r. This arc will be tangent to both straight lines. Using an arc with radius r to connect the 2 sides of a right angle. Example 6, as shown in the figure, given 2 straight lines with a right angle between them, it is required to connect the 2 straight lines with an arc of radius r. Method steps. 1. Directly find the point of tangency using the radius of the connecting arc. Second, then, determine the center of the connecting arc using the radius of the connecting arc. Third, draw the connecting arc between the tangency points. This is one method. In fact, we can completely solve this using example 5's method. Here, we can summarize the method for connecting 2 straight lines with an arc. No matter if the angle between the lines is acute, obtuse, or right-angled, we can use the same method. Draw parallel lines to the 2 straight lines with a distance of r. This gives the intersection point O. Use O as the center, with r as the radius, draw the arc. This gives the desired result. Example 7, using an arc with radius r to connect a straight line and the arc. As shown in the figure, given a straight line and an arc with radius r1. Now, it's required to use an arc with radius r to connect the straight line and the arc. Method steps. First, draw a parallel line to the straight line, with a distance of r. Second, the connecting arc to be drawn is externally tangent to the known arc r1. For two externally tangent arcs, the distance between their centers is equal to the radius. Thus, use the center of circle r1 as the center, draw an arc with a radius of r1 plus r. It intersects with the parallel line we just created at point O. Use O as the center. Draw an arc with radius r. This arc will be tangent to both the straight line as well as the arc. Connection between arc and arc. Example 7, using an arc with radius r to connect two given arcs with external tangency. As shown in the figure, given two arcs with radii r1 and r2, it's required to use an arc with radius r to connect these two arcs, making them tangent. Based on the given conditions, the connecting arc needed to draw is externally tangent to both known arcs. Method steps. Use circle r1's center O1 as the center. Draw an arc with radius r1 plus r. Use circle r2's center O2 as the center. Draw an arc with radius r2 plus r. The intersection point of the two auxiliary circles is O. Use O as the center. Draw an arc with radius r. The drawn arc satisfies the requirements. Example 9, using an arc with radius r to connect two known arcs with internal tangency. As shown in the figure, given two arcs with radii r1 and r2, it's required to use an arc with radius r to connect these two arcs, making them tangent. Based on the given conditions, the connecting arc to be drawn is internally tangent to both the known arcs. Method steps. 4. Use the circle r1's center O1 as the center. Draw an arc with radius r1 minus r. Use the circle r2's center O2 as the center. Draw an arc with radius r2 minus r. The intersection point of the two auxiliary circles is O. Use O as the center. Draw an arc with radius r. The drawn arc satisfies the requirements. Notes: when subtracting the radii of the two circles, always subtract the smaller radius from the larger one. Example 10. Use an arc with radius r to connect two known arcs with mixed connection. As shown in the figure, given two arcs with radii r1 and r2, it's required to use an arc with radius r to connect these two arcs, making them tangent. Based on the given conditions, the connecting arc r to be drawn is externally tangent to arc r1 and internally tangent to arc r2. Method steps. 7. Use circle r1's center O1 as the center. Draw an arc with radius r1 plus r. Use the circle r2's center O2 as the center. Draw an arc with radius r2 minus r. The intersection point of the two auxiliary circles is O. Use O as the center. Draw an arc with radius r. The drawn arc satisfies the requirements. Now, we can summarize. To connect two arcs with an arc, analyze whether the tangency is external or internal first. For external tangency, the distance between the centers is the sum of the radii. For internal tangency, the distance between the centers is the difference in the radii. Both cases involve finding the common center by using auxiliary circles. Fourth, slope and taper. What is slope? The ratio of the difference in height, h minus h, between two specified cross-sections to the distance L between these sections is called slope. It can also be said that slope is the degree of inclination of one line relative to another line. The slope symbol is s. It can be expressed as the tangent value, that is, s equals tangent of beta, which equals h minus h, divided by L. Usually, we set the first term of the ratio to 1, and express the slope as 1 to n in simple fraction form. Now, let's see an example. As shown in the part drawing, we need to draw this figure using a different scale. Except for the contour of the slope, all other contours can be drawn to scale. Now, we just need to complete the slope line, which can be done in the following steps. From the left end of the bottom edge, take a length of 12 units. At the endpoint of the 12 units, take a length of 1 unit in the vertical direction. Connect the left endpoint and the endpoint in the vertical direction. This gives the slope line with a slope of 1 to 12. Draw a parallel line to the slope line from the endpoint of dimension 8. This completes the slope line required in the part drawing. The slope symbol is similar to the greater than and less than symbols in mathematics. The angle between the two lines is 30 degrees. What is taper? Taper refers to the ratio of the difference in diameters of the two cones with perpendicular axes to the axial distance between these two sections. It can also be described as the ratio of the diameter of the cone base to its height, that is, d to h. The taper symbol is C. If the cone is truncated at the top, forming a frustum, the taper value can be expressed as the difference between the base diameter, d, and the top diameter, d, is divided by the height, l, of the frustum. It is easy to see that the taper value remains unchanged. Let's look at an example of taper, as shown in the figure. Draw a shape with a taper of 1 to 5. First, draw the contour shown in the figure based on the part drawing and the required scale, starting from the indicated position. Measure 5 units along the axis direction to get the endpoint. Then, from the starting point, measure 1 unit in the direction perpendicular to the axis to get 2 points. Connect these 2 points and the endpoint. This will give the small cone with a taper of 1 to 5. Next, draw parallel lines to the slanted line. This will complete the contour line of the 1 to 5 taper in the part drawing. Finally, complete the shape. Note that when dimensioning taper, use extension lines from the contour line of the tapered surface. The apex of the taper symbol points towards the smaller end of the taper. The taper symbol is shown in the figure. The taper symbol generally has a 30 degrees angle at the apex. Fifth, drawing ellipses. There are 2 methods for drawing an ellipse, the concentric circles method and the four-center circle method. First, let's look at the concentric circles method. Generally speaking, the lengths of the major and minor axes of the ellipse are known. We can start by drawing the axis of the ellipse. Mark the 4 endpoints of the diameters of the major and minor axes as shown in the figure. Next, we can follow these steps to complete the drawing. Use the center of the ellipse as the center of a circle, with the major and minor axes as diameters. Draw 2 concentric circles. Divide the circles into 12 equal parts. Draw radial lines from the center. Find the intersection points with both circles. Draw perpendicular lines from the equal points on the major circle. Draw perpendicular lines from the equal points on the minor circle. The intersections of the vertical and horizontal lines are the points on the ellipse. Use a French curve to smoothly connect these points to form the ellipse. It can be seen that the more auxiliary lines you draw, the more auxiliary points you get, and the ellipse drawn will be smoother and more precise. Now, let's look at how to draw an ellipse using the four-center circle method. Just like the concentric circles method, start by drawing the axis of the ellipse. Mark the 4 endpoints of the major and minor axes as shown in the figure. Next, we can follow these steps to complete the drawing. 1. Connect A and C, use O as the center. Draw an arc with radius OA, and get point E. Then use C as the center. Draw an arc with radius CE to get point F. 2. Draw the perpendicular bisector of AF. The perpendicular bisector intersects line AB at point 1, and intersects line CD at point 2. Find the symmetrical points 3 and 4 of points 1 and 2. Connect points 2 and 3, 3 and 4, 4 and 1, and extend to get a rhombus. Use points 2 and 4 as the centers. Draw arcs with radius R equals 2C equals for D. Then use points 1 and 3 as the centers. Draw arcs with radius R equals 1A equals 3B. This gives the ellipse. Summary: in this course, we learned geometric construction, including dividing lines into equal parts, dividing circles and constructing regular polygons, arc connection, using set squares to draw arcs, tangent lines, slopes and tapers, and the methods for drawing ellipses. You should master the steps for commonly used geometric construction methods, such as dividing line segments, arc connection, drawing slopes and tapers, fitting irregular curves, etc. Clarify the applicable scenarios using different drawing methods. Be able to accurately distinguish the geometric construction requirements in mechanical part drawings. I wish you all success in your learning.